Today I am very excited to introduce Max Kleiman-Weiner, who is doing a postdoc at MIT and Harvard, and we'll be talking about reverse engineering human cooperation. So please join me in welcoming our speaker.
Thank you so much for having me and for the invitation. It's always fun to be back in LA. I grew up here, so it's great to be back. Okay, so I'm going to share a mixture of work that I did, some during my dissertation, some more recent, and kind of tie it all together with what I hope will be, in some ways, the idea that we can study human cooperation, but from the perspective that an engineer would. So how we might actually build machines that cooperate like people or might cooperate with people, and what kinds of representations, what kinds of processes might go into such an account that we can actually give a formal account of cooperation in the language of engineering. But I'm going to present all of the kind of underlying mathematical formalism at what I hope will be a relatively high level. So any experience you've had with Bayesian statistical methods will help, but besides that, it shouldn't require anything else, and it'll all be very behavioral. Okay. So start with the observation that cooperative behaviors are ubiquitous across the animal kingdom. So here's an example of some weaver ants, and they're all sort of working together to form a little bridge over this gap in space so that they can get across. Some of the ants can get across. And this is important for when they make their nests. Or another example would be packs of wolves that hunt together to take down prey that are bigger than any individual. And then as machines become intelligent and machine intelligence becomes a reality, we're faced with new forms of cooperation between machines and humans, and all of these are different kinds of cooperative behaviors. But when we look at people, human cooperation still seems distinct. Even a young child can cooperate with the scale, scope, and sophistication that exceeds all other kinds of non-human intelligence. A toddler barely able to walk can help others complete tasks. 3-year-olds can negotiate how to divide the fruits of their labor fairly. So you can see that one kid got 3 marbles, and he's about to give the extra one to his friend. These are both work from Tomasello. And 5-year-olds can solve a variety of challenging social dilemmas using turn-taking, rules, and norms. But really, all of these feats are really just a prelude to the unprecedented level of cooperation that underlies social institutions, social contracts, government, science, technology, morality, etc. In some cases, these cultural products involve millions of individuals who are unrelated and who may never meet. So what I want to understand is, what are the origins of this kind of distinctly human cooperation, and how might that help us understand ways in which we can be distinguished from these other kinds of cooperative intelligences. So I start with, in some sense, the basic challenge of cooperation, which is that cooperation is challenging. So even though we'd all be better if we worked together, so if we all cooperated, individuals might be better off looking out only for themselves. And this has been a very basic observation that's sometimes called the tragedy of the commons. One example of this you might think of as taxes. So we all pay taxes into this public good, and the government provides us all with all kinds of public benefit. But from the perspective of an individual, if I could get that public benefit but not pay my taxes, well, that'd be even better for me. So this question, which has really been an active pursuit of almost 50 years of research, is how can we reconcile the existence of that kind of logic of economic rationality or of evolutionary efficiency with the kind of widespread group behaviors that we see, these cooperative behaviors. And this has been studied quite centrally in evolutionary game theory and many other fields for almost 40 years now. And so at its most simplified way to think about this puzzle, this challenge, is through a very simple game called the prisoner's dilemma. And this has been, again, also studied for 40 plus years, where each agent is faced with 2 choices. They could both pick the action cooperate, and that would do what's best for the group. But if they each choose compete, that's best for each individual. And so if you're only playing this game, the prisoner's dilemma, one time, where cooperate gives us each 7 points, but if I cooperate and you compete, you'll get 8 points and I'll get -1. But if we both compete, we'll get 4 points each. So that's how this structure works. And the challenge is that if we're just playing this game once, no matter what you do, I'm better off playing compete. If you play cooperate, well, I can play compete and get 8 rather than 7. If you can play compete, I can get 4 rather than -1. Now, there's many solutions to this kind of social dilemma. One of the most prominent is this idea of tit for tat, or reciprocal, or cooperative reciprocity. And the idea is very simple. You can encode it in what's sometimes called a finite state automata. And the idea is quite simple. It's like an if, then, or else logic. If on the last round you played cooperate, I'll play cooperate back. If you played defect, I'll play defect back. So I'm just going to copy whatever you did. And I'm going to start off by playing cooperate. That's what that little arrow shows. OK. So this strategy seems to encode this kind of reciprocal altruism, this kind of reciprocity. But in some sense, it actually doesn't encode anything about reciprocity. The algorithm that I'm showing you here, it just knows start off playing the first row, and then copy the index of the action that the other person is playing. It doesn't know what the words cooperate or compete mean. It doesn't look at what the payoffs are to each player. It's just a behavioral reflex that has two things that are hand-coded from the start. Now, the human concept of tit for tat in particular, and reciprocity in general, is much richer than what tit for tat can provide. And when we look at what the kind of research that's gone on in what is essentially now called evolutionary game theory, we get this entire zoo of different behavioral reflexes, and each one is just one kind of strategy that works in one kind of particular environment. Now, in contrast, people and other sophisticated social animals cooperate far more flexibly and robustly. We cooperate across many timescales, many different contexts, when we have a whole different variety of different actions available to us, and do that in the context of different kinds of relationships, whether they're defined for us, like kin, or have to be inferred or developed, such as reciprocal relationships. So now, what I'm going to do in this talk is to try to give different accounts of how the kinds of cognition that humans have at a computational level goes beyond this kind of simple if-then or else logic of the tit for tat strategy. And I'm going to do that in kind of thinking in terms of different timescales. So the first being looking at the evolutionary origins. So kind of looking at what kinds of strategies might be supported by evolution in a kind of evolutionary rational simulation, but in a context that requires flexible cooperation, where there's an infinite set of games that you still need to be able to cooperate in. I'm going to very briefly touch on different ways in which, during development, agents might use different kinds of statistical learning to learn different kinds of moral and cultural knowledge and learn it rapidly so that they can generalize different principles of cooperation and how that might vary across different cultures. And then I'm going to start by describing how a lot of this kinds of knowledge and these cognitive processes are used to enable generalized cooperation in the moment. So we're faced with an infinitude of possible situations. How do we know how to cooperate in each one of them? And how do we know who's cooperating with us in those? So how do we distinguish friend from foe? How might we also make judgments about right and wrong? Okay. So I'm going to start again at the top, and then depending on timing, we'll either do both or one of the other two. Okay. So when we're thinking about in-the-moment cooperation or in-the-moment action, social action, we can start with what has in some sense been a sophisticated type way that computer scientists have studied social interaction, which is through games. So, and I like this cartoon from XKCD because I think it kind of gets at what the kinds of games that are often studied in computer science versus the kinds of games that humans are most likely to play. So on the left, it's showing which games are easy for humans, or easy for computers to play, and essentially have been solved by computers. So tic-tac-toe and checkers are in this category. Or games in which computers can beat the top humans, so games like chess and now Go. And what's kind of cool, this comic's now a few years old, all of these games of Jeopardy, StarCraft, poker, Go, and there's another esoteric game. All of these games, based as a result of recent research in AI, have now computers can beat the top humans in. But what I like about this little comic is that there are some games that computers may never outplay humans. And at the bottom here is this one I really like called Calvin Ball. And if you don't know how Calvin Ball works, it's really simple. It's all about an ad hoc interaction. So the rules are really simple. You make the rules as you go. And I think this idea of that human interactions are distinctly ad hoc, they're not zero-sum, they're not necessarily two-player, there's not a winner and a loser, is indicative of many of the other kinds of hard games that are really a key part of human sociality, where the games themselves and what is even the goal of the game is often negotiated in real time. Okay. they're not just about winning and losing, they might be about cooperating and doing better than you might on your own. Okay, so what we've done to try to go beyond these simple tit for tat or prisoner's dilemma-like games is to study what I've been calling naturalistic games, but they're essentially sequential social dilemmas. And they require agents to act over space and time. So let me describe to you how this works. And this is a paradigm I should mention that we've borrowed from the computer science community in multi-agent systems. So there's two players here, the red player, the blue player and the yellow player, and each player is represented by a little circle. That's the avatar. Now on each turn of the game, so time happens in turns, each player is going to choose where they want to move, and they can click up, down, left, right, and they click, and then they confirm that they want to move to that square. And then both players choose where they want to go, and the game then updates. If both players try to move to the same square, then only one player will move into that square, and the other won't. So something like this would happen, and that's just determined by chance. So this time, the blue player won the coin flip, but the moves happen simultaneously. Now, movement's costly, so every time you try to move in these games, you lose a point. And the goal of the game is to move your player into a square that's its own color. So the blue player wants to move into the blue square, the yellow circle wants to move into the yellow square. And when you successfully accomplish that, you earn 10 points. So something like this might happen. And now the game ends. The game ends when either player reaches one of their goals. Okay, so that's how the game. Now I've taught you how these games work. So you might think, well, what does a cooperative interaction look like in these games? And you can think about it for a second, but here's one example of that, where they both move to the outside squares of the game, and they both score 10 points on the same turn. Now, it cost them 3 moves to get there, so they only ended up with 7 points each, but they both earned a positive amount of points. Now, in a competitive interaction, what might that look like? Well, could look something like this, where blue's maybe trying to cooperate, but yellow took that shorter route to that middle square. Yellow only moved twice, so they earned 8 points, and blue didn't get anything, but moved a few times, so lost some points. So we can think about, just like in the prisoner's dilemma, we can draw back onto these games what it means to cooperate and compete. But in some sense, this is doing all the hard work for what essentially cognition has to do, right? We have to go to thinking in a context like this, we have to figure out what does it mean to cooperate and what does it mean to compete. And only then can we reason about those strategies in this abstract space where it's much simpler. But again, that hides this challenge of actually reasoning over, well, what are the specific actions I'm going to take? And there might be many ways to realize that. And also many different payoffs. And essentially, because of the way these games work, you can play them forever. There's an infinite number of possible strategies you could reason over. And the challenge, of course, is to figure out which actions are cooperative and which actions are competitive. And that's going to be important if you want to think about how to build a kind of reciprocity, because I'm never going to observe you picking cooperate, compete. I'm only going to observe you moving around. So how do I then solve that inference problem of going from actions to abstractions? Okay. So the nice thing about these games is that now that I've taught you the rules, if I change the spatial layout of the squares, I can get a different kind of game. So all the same rules apply, but here's now a game that isn't a social dilemma. It's a coordination game. So it doesn't matter whether the agents say go clockwise or counterclockwise. As long as they end up going the same direction, they'll both score the same amount of points. There's no tension between the group and the individual. But now there's an interesting coordination challenge, which is that if it's their first time playing this game, they might not know, should we go clockwise or counterclockwise? And now there's a real risk of miscoordination. And if you play this out, right? So now blue won that coin flip where they miscoordinated, and blue's now one square closer to the goal. So now you might think, well, blue could wait, can not move, and then let yellow catch up, or blue, if they don't care at all about yellow, might just go for the goal. So something like this could happen, and then you think, oh, well, maybe blue is actually, even though they didn't have to, they're acting somewhat cooperatively because they let yellow catch up and score some points. So we have these two types of games. And again, we can create even more. So I'll just show you a few more examples. So on the right, we have a challenging coordination game, and this is just one coordinated strategy of how they would both score points in this game. On the left, we have another social dilemma where one has to wait while the other goes around and gets into position. So a competitive strategy might look something like this, where blue moves out of the way and yellow goes straight into the goal. Or a cooperative strategy might look like this, where yellow waits and then they score points together. They can't move through each other. I didn't say that earlier. Okay, so we can generate a whole set of these games. We can try all different configurations. We can even randomly generate some. Now let me show you what. So and then we've developed this in an online platform. We can match people online over mTurk, and they play with each other with no communication besides whatever actions they take in the game. There's no way to chat. Each of them is familiarized with the rules of the game before being matched, but they essentially have no. But they're matched with someone that they'll never. They have no idea who it is. It's an anonymous interaction, and it's all incentivized where the points eventually convert into a bonus for the participants. So here's one dyad of people playing this game. And this particular pair was really good at the game. They've just cooperated from the onset and did so quite effectively every single time. So just showing you a few examples. So what you're seeing, that little circle that comes out is where they want to move. It's where they clicked. So this was a slightly older way of replaying the data. Okay, and then they're now put into a new game they've never played before. So they played a few rounds of that first one, and now they're playing this game for the first time. And again, they just in the moment figure out a new strategy that is successful for this particular dyad. Okay. So these guys were really good at cooperating.
Can I stop?
Yeah.
In this video that you're showing right now, blue keeps being the one who goes down, so blue is taking a bigger hit each time.
Yeah.
Does that, like, in cases like this where they have to, do they alternate strategies, or does one continually play the role of?
Yep. So we've seen both in the data, and that's it's one thing that I have some simple tools to model that, which is basically just saying like, well, if we solved it successfully, solve it again, and I've played with models like that. But one way of solving, basically figuring out how to do these symmetries where one player needs to go down or one player needs to go around the other, and then the question is, well, how do we decide on who, is really something that I'm hoping to study in the future. Where, and again, like how do you represent turn taking or other kinds of more abstract norms and roles that agents might emerge quite naturally without any kind of communication because they work well and then stabilize. So that's something that I'm quite interested in, but haven't formally studied. But it's not all perfect coordination. So at the end of the study, we asked people to give some feedback and ask, how they described how they played the game. And this participant said, well, we tried to be cooperative the majority of the time. There was some competition. It really brought out the best and worst in both of us with a sprinkle of luck thrown in. This was very much like real life. So then I was really curious because this was like exactly what I was going for. So I wanted to, right, so I looked at their interaction, and it was something like this. So this is a kind of a fun game or a fun level where they have to create this gap between the two of them, and then they can both get into the goal at the same turn. But if they both kind of move together, yellow will get there first. So this looks really great. Yellow's waiting. They're both moving together. They both score points. And now they're in this tricky social dilemma game, right, where one has to go around the other. The first round, it looks really good. So blue went around yellow, taking a higher point toll. But now something happened, right? So blue is now just trying to move directly into the square, but yellow is like, well, I don't know what they're thinking, but maybe thinking, well, we went around last time. Yellow moved and blue went directly in, and now you can kind of see cooperation is just fully broken down, right? They're both just, and every time they click this, they're losing a points, right? And so this goes on for quite a while. I think the most number of turns in a single game was around 80, and that's like a lot of interaction. That's like a few minutes of just like clicking the screen over and over again. So you can see this keeps going. Okay, so it really was frustrating. Okay, so we started with this problem. What happens in the repeated prisoner's dilemma? And then the answer looks something like that has been given is something like tit for tat. But what happens when we have a game like this that's repeated? What might the answer to that kind of a challenge look like? And that's sort of what I'm hoping to answer. So, and this challenge really has these three different types of points, which I've alluded to, and I want to just state clearly here. In order to reason myself of how do I want to cooperate, that's a high-level choice. Do I want to cooperate or compete? But I have to figure out how to ground that or realize that high-level plan in terms of a low-level implementation, to ground those actions, that goal into a set of actions. If I want to plan reciprocally, I need to infer what is your intention. Do you intend to cooperate with me, or do you intend to compete with me? But I don't observe your intentions. So I have to infer your intentions from your behavior. There's an inference problem. And then finally, in order to be efficient, we have to coordinate our cooperation. So in order to figure out all the different ways in which we might split up the task or do the right role in the task in order to learn how to cooperate effectively. And some of that might come down to learning norms, and I'll show some examples of that. Okay. So to start off with, I'm going to think about, well, what might it mean to ground competition, a competitive interaction? And the idea here is one that we have essentially taken from the behavioral game theory literature, where they've developed models, just to name a few words in case it rings any bells, cognitive hierarchies, or level K reasoning, or sometimes called iterated reasoning. But just to explain what that means, what it means is I start off with some model of you, and that model of you is non-strategic. So maybe it's you moving randomly, maybe it's you pretending I'm not there. It has no strategic action. And so since that model has no strategic parts to it, I just can basically directly simulate what you'll do. There's no recursion. There's no what do you think, I think, you think, I think, and so on. Because we're basically going to unpack that. So I start off with this level 0 model, and then I think, well, if you're going to act in that unsocial way, how might I best respond to that actor? And then we can do that a few times. So like a level 1 actor would best respond to a non-socially sophisticated model. Now, so now what this program is going to take in is the state of the game, S, and this intention, I want to compete. And it's going to give out a distribution over actions. So it's going to say, given the state of the game, given my intention, what actions should happen next? Okay? And it's going to do that selfishly, because this is competition. Just do what's best for me. I'm not going to go through this, but this is just basically extending the Bellman equation and the reinforcement learning formalism to that kind of level K. So that's all I'm going to say about that. Okay. But the key to going further in this through the math is just the thing on the right. Get the actions given the intention. There's lots of, okay, so that's our model for competition. Now there's lots of reasons why we might think cooperation is going to be quite different. So for example, Michael Tomasello has talked about shared intentionality, that humans are able to coordinate with others in ways that other primates may not be able to, like forming a we. Michael Bratman and Searle have talked about shared agency, that having the intention to do something is very different from having the intention to do something together, and entails all sorts of different other things. A collaborator of mine, Nick Chater, has talked about virtual bargaining, that participants might behave on the basis of what they would agree to if they were able to explicitly bargain. And I think all of these are suggestive that when we're reasoning cooperatively with other agents, we're using different kinds of processes that aren't just, if you do this, I can do, if I think you're doing this, I can do that and get what's best for me. That it's not just about prosociality, but actually about a different kind of reasoning. Okay, so let me go through the same sketch of how we might do that. So here's our model for cooperative planning. So it looks just like the other one, except that now the intention is to cooperate, given a certain setup. And again, we want to say, well, what actions will realize that intention? The idea here, unlike that level K, where I'm doing whatever you're going to do and I'm going to do one level better, is to say, well, what should we do? And the idea is like zooming out and thinking from a third-party perspective, what actions would a puppeteer take if it could control both of our actions in order to achieve the joint reward, the best joint reward? Now, each agent can simulate that puppeteer and think, well, what should we do? And then given that, what should we do, it can extract, well, what should I do? How do I play my role in that joint plan? Okay? Now, there's no, just to go back to your question, Erica, we're not building anything about roles or norms here, but a lot of that kind of behavior often emerges just from the efficiency of what the joint action is, okay? Okay, so we have these two types of planning, cooperative and competitive. One is based on this recursion, one is not. It's just about kind of zooming out and thinking, what should we do? But then there's the question of cooperate or compete. Okay, so how do we do that? How do we do that? And how do we think about solving that inference problem I alluded to? And what we're going to do is we're going to extend a Bayesian model of theory of mind to handle this. And so here's what it looks like. And let me just walk through this quickly. I start off with a prior. How likely do I think you are to be cooperating, and how likely do I think you are to be competing? What I want is, given I saw you take a bunch of actions, what's the likelihood, or what's the probability that you're cooperating or competing? Right? That's the posterior. And then I start with the prior over there. That's the far thing on the right. Now, what I need to tie these two together in order to update based on the evidence that I've seen is to say, well, given if you were cooperating, how likely was the action that you took? If you were competing, how likely was the action that you took? And that's that middle term. That's the likelihood term. Now, what's powerful about this, about a model that has these internal agents, this kind of internal agency within it, is that the planning models are both models of how should I act, how should I cooperate, how should I compete, but they're also models of action understanding. So they allow us to go backwards. Because the model here, right, is saying, given that I want to cooperate and the state of the world, what actions should I take? That's exactly what we need in the likelihood terms. So these planning models play a dual role. Okay, and then the idea is based on those inferences, you can decide to reciprocate. So if I infer that you're cooperating, I'll cooperate back. If I infer that you're competing, I can compete back. So kind of imitating that same kind of tit for tat logic, but now it's no longer about the actions of the game, but rather about an abstract intention. Okay. All right, so I'm going to briefly go over 3 different behavioral experiments we did with this model, and basically to test different ways in which this model might actually be a good account for how people play these games. And in the first game, in the first experiment, participants just played 30 rounds of the same game with the same partner. So they're in this repeated interaction, but there's different games now. There's not just one. Okay, so here's this social dilemma game, one of the ones I showed you. And what I'm showing you here, this is just the data from people. And on the x-axis, each point is a new trial, because they're playing 30 games in sequence. And what I'm plotting is these two, essentially, so if you look at the red line, that's all of the data, the average time that both players reached the goal. So we need some behavioral measure of cooperation in these games, right? Did they cooperate? Well, if they both scored points, they must have both, it's likely they did some kind of cooperative action. In red, you can see that's basically flat, right? But if you split that based on based on the average rate of cooperation, you get these two nice clusters, right? So you get one cluster which over time learns to cooperate quite quickly. That's the blue line, and another cluster which over time does not. Essentially never cooperates on these tasks. Now we can do that for a variety of these different games, and we get different curves and different ratios, right? So in this coordination game in the middle, most agents figure out, well, if you're going clockwise, I'll go clockwise too, right? Okay. And same for the bottom graph as well. Looks more like the top social dilemma one. Now, when we have our model make predictions at the dyadic levels to say, predict, what will the next action be? So it takes in all the previous interactions, then predicts the next action, then takes in the real one, and then updates, and then predicts the next one, and so on and so forth for 30 rounds. What you get is a pretty close correspondence in terms of the overall trajectory. So the agents that are cooperating is able to predict, yes, the cooperation is going to go like this. Now, there's other ways we can look at this. So now, what I've done is across all the dyads, I'm plotting over those 30 rounds, we can get the proportion of rounds in which they cooperated in. So if they cooperated in all 30, that would be a 1. If they cooperated in none, that would be a 0. And we get different distributions for the different games. So for some of these social dilemma games, we get these almost bimodal-like distributions, right? So the top and the bottom ones, where some agents, some pairs never cooperate, and some cooperate at relatively high levels. And for these coordination games, we get something, at least for this easy one, we get something much more unimodal, right? Like all agents essentially either figure out how to cooperate at a relatively high level. And our model makes that same distribution. Now, since I'm averaging over the particular groups, right, that could just be kind of a pattern. It's not making, I still haven't shown you anything about an individual dyad, how well we're able to predict that. And so what we did next is we looked at, well, how well are we predicting for each individual dyad? So what I'm showing here is each dot is one dyad, and the model's predicting how well that dyad is going to cooperate, whether it's going to be high or low in a quantitative way. And then the y-axis is how the rate of cooperation in that particular dyad. So you can see in the full model, it actually does quite a good job of predicting at a quantitatively fine-grained way the rates of cooperations of the different pairs of participants in our experiment. And when we lesion the model, so that it doesn't have access to both of those modes of planning, the cooperative and the competitive one, it does far worse at predicting the play of the agents. Now, I think one interesting thing is that in the two social dilemma games, it actually like really fails hard, right? So you can see those basically, almost goes to 0, right? And part of that is because without the ability to switch between cooperation and competition in a dynamic way, there's no way it can capture both sets of the people who cooperated and the people who competed, right? Okay. Now, all of that is suggestive that this model is capturing some of the flexibility that people have. But in a second experiment, we went to look in a slightly more precise way, in a more quantitatively precise way, just looking at that action understanding component. So what we did is we showed people little kind of videos of other agents playing, and asked them to rate the cooperativeness of each agent. So what I'm showing you here is the colored bars are people's judgments, empirical judgments of cooperativeness for the blue and the yellow player, and the black bars are the model predictions. So what they saw was, so you remember they both start off, and here now they've both already moved one move out, and both the model and people are predicting cooperation. Now, and it just sort of goes up as they reach their goals. Now, in this case, blue moves into that center square, and yellow moves, this is like from the demo I gave you in the beginning, and again, people have that intuition that when you see just that one action, no one scored any points yet, they already are able to make these really rapid inferences about the cooperative intention. Now, if blue waits and then gets to the goal, waiting for yellow, then it's clear they're both cooperating, but if they don't wait, then it's clear that he wasn't cooperating. So that ambiguity is because of the kind of statistical inference we're doing, is able to be kind of rapidly and flexibly corrected. And then there's a bunch of other scenarios where the model also does well. We've done this in a bunch of different scenarios, different grids, and again, the model's capturing a lot of the kinds of behaviors that people do at a relatively quantitatively precise way. Okay, now finally, the situations I showed you were simple in the sense that you could imagine a case where I'm not necessarily tracking your intention, but I'm just thinking, did we both score points in the last round? That's one heuristic you could use to get a cooperative intention that's far less complicated. So what we did is we introduced a new feature, and we call these little dotted red lines fences. And the way fences work is that you only have a 75% chance of moving over the fence. So it's not deterministic anymore. You have a 25% chance of getting kind of bounced back and you stay where you are. So now watch this little video and see if you think blue is cooperative or not. Nope. Okay, so they both scored points, but blue kind of tried to get in there as quick as he could, but it just didn't work out, right? Because the fence got kind of a bad roll. Now we had people play this game where we can now dissociate the intention, conditioning on the intention versus conditioning on the outcome, right? And what we found is, and this is a model-based analysis, so we have essentially the way we're able to compare, say, what model best describes people is we have a whole suite of different agents, some the full model, some lesions. So CC agent is this intention reasoner, the one I've been presenting this whole time. We have agents that move random, we have agents that always cooperate, agents that always compete, agents that condition on the outcome. And what you can see based on, and then on the x-axis, each bar is a participant, and what I'm plotting is the marginal likelihood of that model, how well it explains the data from that particular pair of people's interactions. And what you can see is, just like before, some people never cooperate. That's all these big red bars on the right. But of the people who do end up in some kind of flexible interaction, it's much better explained by the CC agent than, say, that outcome agent, which was in brown. Okay, although there may be some, that's not true for literally every pair of participants. Okay, so I started by showing just these two ideas, cooperation and competition. But one cool surprise is that there's, and of course obvious to everyone, is that there's far more interesting, or there's a far bigger space of social intentions one might have besides just, do I want to cooperate or do I want to compete? And this was a sort of surprising dyad that just I saw while looking at what people did. And that motivated some future work I'll briefly show. And what happened was this. So they had not been cooperating. They'd been fighting for that middle square, and then one person would go in, and then next round. Okay, and then this happened. So they, just like before, they kind of fight for that middle square, and then blue went into yellow square. Nothing happens, right? It's just fine. It's fine. Okay, then I'm not sure exactly what happens, but then we see something like this. And after this round, they started cooperating again. They started cooperating and did so robustly till the end of the experiment. So what's going on here? So one thing it could be is, well, maybe blue is trying to punish yellow, and that's why it's like payback, and now and now you're gonna, by punishment, you're gonna figure out that you need to cooperate. That would be this sort of tit for tat like logic. But I don't actually think that's what's going on here, because there's much more effective ways to punish yellow, right? In this interaction, yellow actually got all their points. Had blue gone into the blue goal before yellow made it, that would have been far more punishing. So I actually think this may be something more like blue showing yellow what they want to do, what they want yellow to do. And so that's one possibility. Now I'm going to quickly go over a few other papers that we've written in similar paradigms. So it's going to be less detailed, but I just want to kind of show you some of the other ways that this has inspired some of the more recent work I've done. So here's a case where the blue agent is either going towards the blue goal or the red goal. And one challenge is, does that agent, and this kind of feeding back on the last example, does that agent want to share what its intention is, right? So let's say you're trying to figure out what goal this agent's going to. And it could go this way. And if it did, as soon as it moved here, you would think, oh, it's going for the blue goal. But if it's going here, you'd be like, oh, well, I'm not sure, because once it gets here, it can make its choice, right? So we developed a model where agents can learn policies to either share their intention, to include as much information about what they're doing so that another can easily infer it, or to hide their intention. So to minimize, to achieve their goals, but do so in a way that limits how much has been shown. So this is just kind of showing the paradigm that we looked at this in. And then what I've shown you, in the last long set of experiments I showed you, it was all about cooperate or compete. But once you go to a scenario that involves more than two agents, so here's the same kind of 2D grid world, but now there's three. So each of those circles are a different hunter, and this is a stylized, spatially and temporally extended stag hunt, for those familiar, where the stags move away from the agents, and in order to catch one, they have to both they both have to get it at the same turn. Or they can get the hare, which just stays there, right? But it's a lower reward. So once you have three players, it's not just cooperate or compete, but it might be cooperate to compete. So it might be these two of the players might actually want to cooperate with each other. And when you think about, and what we did in this paper was to say, well, when you're doing these inferences, it's not just about cooperate or compete, but actually kind of parsing the whole social scene into a graph of relationships and ideas. So we can get back what we had before of like agents best responding to each other, but we can also model agents B and C best responding to agent A, kind of cooperating to compete, and then A being sophisticated and doing what's best for himself, given that they're teaming up on him. And what we did in an experiment where we showed people these scenes unfold over a few time steps and asked them to make inferences about who's on whose team, like who's working together. And it could be everybody, it could be just one of them, it could be nobody. And so on each time step, this is a person making the inference over the three possible teams that could have the three teams that were possible, and then the model's making the same predictions, using the same inferential techniques. So you can see again, the model does a pretty good job here, and then across, again, the power of the model is that it's abstract, so we can study it across a variety of different worlds, and again, the model is kind of capturing a lot of the fine-grained variance in people's judgments. Okay, now finally, this is I guess the newest thing I'm going to show today. This is a paper we submitted a few weeks ago, which is really to push less on the challenge of cooperate or compete, but really on the challenge of just cooperate. Because when you know you're in a cooperative scenario with someone, it's there's all kinds of challenging things, like who should do what? Should we do tasks in parallel so that we're like kind of working on the same so that we're like, maybe we can complete the task twice as fast? Or should I help you complete your task fast, and then we'll move through the task list twice as fast? So these are these games. I don't know if anyone's here's played the video game Overcooked. It's a fun multiplayer game. But we made simple 2D versions of the game where each agent's a little chef. They're in a kitchen, and they have to complete a recipe. And so here's at the abstract level, all the high-level steps. So you have to get the tomato, chop it, put it on a plate, serve it, right? Okay, so things like that. So here's one way that these agents, and so this was a CS paper. So we just looked at building an agents that can effectively coordinate in these ways. So here's one way, right? So this agent's chopping the lettuce, this agent's chopping the tomato, and they both kind of have split up the task of chopping a tomato and serving it, and chopping a lettuce and serving it into one does each one takes one kind of sub-part of the tree. So that's one way you could solve this task. But another way you could solve the same exact task is to have them work together. So the red agent is doing all the chopping, and the blue agent is helping with the plating. Okay, so, and again, the same inferential technology, that same idea of I have a model of what you're doing, how can I best play my role in this joint plan using that idea of the kind of the puppeteer is the same thing underlying these inferences. Now what's cool about this is that in some cases, maybe in this game, in this level, it doesn't really matter how you split up the task. But here's another world where now there's this big divider. So that allows for a whole different kind of set of strategies. In some sense, they have to, the cooperative strategy that they end up with is going to look far different. So what we did is we kind of combinatorially change both different kinds of recipes, right? So different things they have to make in different worlds. In this world, each agent can do the task on their own. It's just how do they mesh together. In this case, they better work together because they have no way of getting to the other side, right? They have to work together on each task. Okay, so just showing some, and we're hoping to use these models to now study cooperative behavior in people in the same way I showed you before. Okay, and then just lastly, a recent paper we had on taking these same ideas but really scaling them up. So this is a board game called the Resistance Avalon. It involved, the whole game is essentially, it's like Mafia or Werewolf, where there's the good guys don't know who else is a good guy. There's the bad guys know who's a good guy and who's a bad guy. The good guys need to figure out who the bad guys are based on their actions in the game. The bad guys need to hide who they are so the good guys don't figure them out. And it's a nice game, it's a lot of fun to play with friends. Basically, it's all about deduction and deception, and we were able to scale up the techniques that we developed that I just showed you in order to actually play this game at a superhuman level. So if you're interested in that kind of idea, you can check out this paper. Given how much time's left, I think I'm going to skip the developmental part, and because I want to show, I think for this audience, maybe the evolutionary stuff is more interesting. So, and I'll go through this relatively quickly so we can have a lot of discussion. Okay, so I showed you these models. I showed you how they might be good models for understanding human cognition and human behavior. But tit for tat had this really strong grounding in these game-theoretic ideas that tit for tat is an equilibrium. Axelrod played all these tournaments, and tit for tat came out on top. What about these models? Are these models good? Right? Are they good in that evolutionary sense? Yep.
I was going to say, you probably have 20 minutes if you want to if you want to show both of them.
Okay. Should I?
I mean, it's totally up to you.
Okay, I think maybe it'll be fun to do both then. Okay, so let's just go back. No, that's fine. Okay, so. Soon you'll see the evolutionary grounding of these models. But first, the things I showed you were in some sense limited to the context of put in this environment with people I've never interacted with before, and we have to figure out cooperation, right? It's all anonymous. And that's really not at all how the human social world in particular, and I think a lot of other animal sociality as well, works, right? So. Instead, what we have is a much more generalized sense of how we should weight and value the other individuals. And so formally, you can write that down very simply. This is this idea of a recursive utility calculus. So it says, for agent I, let's just call that me for now, I weight, it works perfectly, I weight my reward, so the things I want, but I also weight the things that other agents want. And in particular, I have some weighting on those, so I'm trading off what others want with what I want. So this is a very simple idea, right? Okay. You can trace it back to even Mill, I think. Okay. So the challenge is how to set that alpha parameter, right? What does it mean? How do I know how much weight to put on another individual? I can value myself, but we have all these different ways of thinking about how we might value others. And if I can set that alpha in a reliable way, well, that might really generalize, right? Because I can think about, I can weight others in a very flexible way where I might not need to see you behave at all, and I might already value you as maybe as a brother, as a person, as whatever. Okay. All right. So we set out to sort of add some formalism to the challenge of how might a child figure out how to do this. how might they figure out how to set that alpha for every person that they interact with? And we called this, the idea as like a common sense moral theory. It was a quote based on, I think, J.L. Austin. But the idea is that it's by Thomas Nagel. But the idea is that a common sense moral theory is really just a system of values for trading off the interests and welfare of different people, self and other, friends and family versus group versus the larger society. People, then all these reciprocal ways of trading off welfare, like should I be good to those who've been good to me previously versus those who I've never met versus those who might be good to me in the future. And the key idea here, and I'm going to keep this at a relatively high level, is that different societies and different places and different times have differed in how they make these moral trade-offs, right? So in some societies, you might think that preferential treatment of kin is a kind of corruption or nepotism, but in another society, they might see this as a moral obligation. Like, what kind of a monster would hire a stranger instead of their own son or daughter? Okay. Some cultures. Oh, so right. And I have a quote from Trump here saying on the Larry King show, saying, "I like nepotism." You know, a lot of people say, "Oh, nepotism." Usually, these are people without children. So, you know, even within a given culture, you have many different ways of valuing these things. Group loyalty versus impartiality across groups. And then, of course, there's tons of diversity at all levels of any society. And all I can say is that I am that is like a real characterizing that is a challenge that I've only read a little bit about, but that the diversity is pretty well known to exist, both within and across cultures. And because of that diversity, there's a challenge for learning, because I don't think it's very controversial that in generation 1 and generation 2, there's that much there can be difference, but in many time periods there's not, right? So there's a challenge for learning. How do we get these stable cultures, and how might they change too? Okay, so the idea was to take the same kinds of ideas, the statistical learning framework, and say, well, one kind of data that all individuals get is they get to observe adults who already know the right way of doing this, and they get to observe them making decisions and judgments about what those individuals think are appropriate trade-offs. But the challenge again is that it's noisy, because the actions that individuals take only noisily or indirectly reflect the underlying moral theory which led to that action. So here's an example. You have this guy, he's helping out this other, he's behaving in some kind of altruistic interaction. Is he doing it because he's just a generalized altruist? Is he doing it because he wants to help out white people? Is it because he wants to help out Americans? Is it because that guy helped him out 30 years ago and now he's paying him back? There's so many explanations for the cause of this altruistic behavior. If you're just watching it, you have this hard inference problem to solve. And so the idea was that moral learning, like language learning, confronts children with a challenge of that Chomsky called the poverty of stimulus, right? That there's a gap between the data that's available to the learner and the kinds of inferences that the learner makes from that data. So for example, we're all very comfortable making decisions like, what should the self-driving car do when faced with this complicated trolley problem? Should it swerve and kill one, or should it run over 5 people, if you're following the news? Now, none of this has ever happened. None of us have any experience with any kind of situation like this, but where we have this very flexible moral apparatus that allows us to generalize these kinds of problems. Okay. Now, the challenge of that, starting with this equation, is essentially a statistical learning problem, which is the curse of dimensionality. If this is what's going on in people's heads, we would need 6 billion different alphas in our head, and we need to learn how to set each one of them. And that just seems impossible. Now, it's impossible that we'd get data on all those people, so that's in some sense a non-starter. But even if we did, if we got data on like 5 billion, we'd then have no idea what to do with the other billion, and that also seems completely artificial, right? Instead, what we do is we're able to use different kinds of abstract moral principles to make this learning efficient, sample efficient. And then the solution to the curse of dimensionality is something called the blessing of abstraction. So the idea was to introduce structure to this alpha parameter and say that actually this alpha parameter can be set by more abstract features of that the individuals might share. So is agent J the kin of agent I? Well, then they might learn, well, you should weight kin in a generalized way, or weight your in-group in a generalized way. You might, and the same for these reciprocal relationships as well. Now the challenge of moral learning is operating over a far lower dimensional space. It's not on this vector of 6 billion alphas, but rather on this much lower dimensional space of moral principles. And what we showed in this paper was that based that a model that gets a bunch of, in the same setup I gave you, a bunch of different observations of actions and judgments can figure out the alphas by going up another level of the hierarchy, by figuring out how to weight the principles. Okay, and so the key idea was, again, the same underlying math, right? Which is that Bayesian theory of mind idea, that based on I have some prior over the kinds of values an agent might have. Based on those values, I can think about what an agent might do, and that's the likelihood. And then from that, I can compute a posterior. Given that I saw you take a set of actions, what are the values that might have driven your behavior, and handle all the noise effectively. Now, just because I'm able to infer your values doesn't tell me how to set my own values. And here we were inspired by some philosophers, which this idea that learning and acquisition is really a challenge of alignment. So how might I align my moral values to the values of others? And we call this external alignment because what it basically says is that what you want is you want to value having the values, so minimize the difference between of those that you value. So you want to make your values as close to those that you already value. Okay. Now, external alignment can explain, and we have a bunch of simulations in this paper to show, can explain how a moral theory can be stable over time. But it can't explain rapid moral change. So what we've seen is that in just a few generations, attitudes towards, say, for example, same-sex marriage have changed quite rapidly over just a few generations. Another nice recent study was that changes in prejudice towards trans people change after just a single 10-minute conversation, right? So it seems like if we're just doing this kind of noisy copying over time, it's unlikely to explain this kind of rapid moral change. And so again, inspired by some philosophers, Campbell and Kumar, we posited this second motivation of internal alignment. And the idea here is that you have some external source of valuation outside of morality. Maybe it's feelings, maybe it's you read a story, maybe it's you've somehow been humanized to a certain plight of an individual. And those feelings generate an inconsistency between the feelings that you have and the principles that tell you how much value they have. So think about the example I like to use is a father who's homophobic but has a son who's gay, right? So there's an inconsistency. And so something has to change. And this motivation says reduce that motivation. And I, because of time, I'm going to refer to the paper to see all the simulations that we ran showing how these things work. Okay, now just to go through this kind of quickly too, this is some work I did with Alex Shaw on thinking, well, okay, we have this equation, now we have some way of setting the alphas, but it's still, we're stuck in this linear, what you get, what I get, what you get, what you get, what you get, just a big long chain of welfare. But we know, of course, that people don't just weight the value of others linearly, right? We care about the distribution. We care about, people get what's fair or what's equitable. Now, what we looked at in this project was that there's a lot of evidence that humans aren't just looking at how, at the distribution, but how their behavior will be perceived by others. So we care about our reputations, and we want to be seen in the right light, right? So, and that being seen in the right light can shape the kinds of choices that we make. So this is, I think, well known to, or a better way to say it is maybe Bert and Ernie can say it best for me. So here's a short clip that is fun.
Look here, Bert. I have 2 pieces of apple pie, Bert. Would you like a piece of apple pie?
Oh boy, would I? Yes, please.
Oh, okay. Let's see. Let me just look at these for a minute. Okay,
Smell
Bert.
that apple pie.
Yeah, you take that piece there, Bert, and I'll take this piece here.
Excuse me, Ernie, but Ernie, you gave me the small piece.
Oh, well, that's true, Bert. That is the small piece there, and this is the big piece. And I gave you that piece, and I think I'll keep the big piece myself.
Ernie, that is not very polite.
Well, how do you mean, Bert?
Well, I mean, if I had 2 pieces of pie, I'd offer you the big piece and take the small one for myself.
Well, Bert, you have the small piece, Bert.
Okay, so what does Bert understand that Ernie doesn't, right? He understands that when you make a choice, you're thinking about what does that choice say about you, right? Okay, so again, we modeled this in a similar fashion. I'm just going to go through this very quickly. The same idea. You have some low level, you have some kind of basic level, outcome level values like inequity, but also efficiency. But others, you're thinking, how will others perceive me? Will they perceive me as valuing one agent more than another, being partial versus impartial? And then you can model these higher order social values by constructing them from, again, the same kind of math, that same kind of theory of mind, right? How likely are you to infer that I'm partial based on my actions? And we unwind that, and then include those inferences in the agent's utility themselves. So they want others to be, you want another person to perceive you as impartial. Okay, and then we ran a bunch of experiments. I'm going to just go through this quickly because I want to show you the evolution stuff. Okay. We also looked at some fairness, accuracy. This in the context of fairness and accuracy in a variety of different ways. Okay. Do I have like 8 minutes? Is it good? Yeah. Okay. So, okay. So I showed you all these different. Okay. So we wanted to study, say, well, how might all of these different pieces fit together, right? We have this idea of an abstract and generalized tit for tat that can explain kind of something about a dyadic interaction. We have these much more generalized utility calculuses that can like work with all different kinds of things going on, can learn from observation. And how can we then take all these different models, which might account for different pieces of human cognition, but to ground them in something more like a rational analysis? So in the logic of evolution, the challenge I started with. But to do it in this different way, right? To start with the same challenge. Humans never play the same game twice. Our interactions are infinitely varied. So what might be the right paradigm to study that, and that has the right kind of simplicity and complexity? So what we did is we developed this thing that we call a game engine. And basically you can think about it as like, it generates game-theoretic interactions. They're all very simple. You have some pool of players, and the game engine spits out a sample from this game engine is a different kind of social interaction. So for example, one sample would be A pays 1 to give 3 to B, so that's like some costly prosociality, or do nothing, right? Okay, that's one thing. It could also be A could give 4 to A, or 4 to C, or do nothing, right? So no cost to B, some combinations of the two, and essentially all the costs, the benefits, who's involved, how many players involved, how many actions there are, all of that is going to vary across each interaction. Okay, so again, we had the problem of prisoner's dilemma, we had tit for tat, we had the problem of these naturalistic games, we got this cooperate compete framework. What might be the solution to something like this? And again, I think the idea is just going to go more and more towards a more abstract theory of reciprocity. So again, we're going to start with these utility functions. And now we can think about different types of agents. So the first is a selfish agent. They only care about themselves. Simple. I only care about my reward. Only cares about I's reward. An altruistic agent is maybe similar to the one we were looking at before, is very simple, but it's a simpler version. I cares about its own reward, but also cares about the reward of everybody else. Okay, so it's just totally prosocial. And then we can think about, well, what makes a utility function rational or well adapted? So is it that it achieves the best outcome when playing against itself, like the altruistic agent will, because it's always going to do its best for the group? Or when it is playing against anyone else, which is like the selfish agent, because it's always going to do its best for itself? And the idea is that in the social world, the environment is itself adaptive, right? So just to play out the logic of evolution for a second is, if we all started out altruistic, but if one selfish agent ends up being in the mix, they're going to exploit everybody because the altruistic agents, they just unconditionally value everybody. So if there's some kind of cultural or evolutionary dynamic over values, people are going to say, well, that selfish guy is doing really well. I want to copy what he's doing. And now all of a sudden you've shifted the equilibrium towards this, everyone's playing the selfish strategy. So we need something like reciprocity, not just unconditional altruism, to explain how we can start to do evolution over this value space of utility functions. So what we did is we developed this reciprocal agent, which is really based in large part on all the different stuff I've showed you before, and you'll see how it builds on it, which says, I care about my own reward, but I also care about the reward of others, and I do that proportional to my belief that the others are also of the same reciprocal type, that you are also reciprocal. So it has that kind of circular logic that all of this stuff has, and I'm going to show you how we're going to break that. Now, the challenge is, of course, that you don't observe, unlike behavior, theme of this talk, you don't observe the types of other agents. You don't observe what their values are. You have to infer them. That's going to require this cognitive capacity. And again, same kind of setup, right? We start with the type of an agent. We generate actions by doing some kind of expected value maximization. And then that inverse inference, given your actions, what's type are you, is going to go through that same kind of Bayesian framework. Okay. So just quickly, one of the challenges here is that for this to work, requires agents not just to have models of other agents, but to have recursive models. They have to say, well, not just what do I think of A, but also what do I think A thinks B thinks, and so on and so forth. And so something like that. And in order for this to all work out. And what we showed is that we were able to develop a new way of accounting for these recursive belief dynamics by thinking about joint belief, which is related to common knowledge. And the idea is that just the high level idea, ignoring the slide for a second, is just that if we both observe what happened, we can just think about what do we believe happened, rather than me thinking, you think, I think, you think, and that kind of goes ad infinitum and diverges quickly. If I just think, well, what do we think? What do we both know about the reputation of that individual? We have these much more stable inferences, and it simplifies how to update reasoning about knowledge in these large groups. Now we can test this over the time scale of just a few interactions. So what I'm showing you is an agent interacting with a selfish agent over 15 interactions, and you can see very rapidly it learns. The player I'm interacting with is a selfish type, and that's true for all these other types of agents as well. Now we put these agents in an evolutionary setup where they're playing this game engine with each other. Each one's matched with a different dyad. They play. It's sort of like a repeated prisoner's dilemma, but the game's not the same. And there's a Moran process which governs the evolutionary dynamic, basically saying agents that are performing better are more likely to have their type copied in the next generation. And what I'm plotting here is the steady state of the population as a function of the number of times each agent interacts with each other agent. So this is that standard direct reciprocity setting that, like in the Axelrod tournament. And what I'm showing here is where you see a lot of red, when the number of expected interactions is very low, the selfish agents dominate, not surprising because it's like a one-shot interaction. But even just after a few repeated interactions, the blue agent's able to win quite stably and reliably in that population, right? So we can maybe say like this reciprocal strategy becomes rational in this repeated setting. We also showed that it's robust to noise, so when you make the actions a little bit noisy, these agents can reason about that because again, they're doing this probabilistic reasoning. So okay, we designed a new agent to play this new kind of game. It worked pretty well. But what we wanted to then look at was, well, how might this agent compare when we put it back into the world of repeated prisoner's dilemma, into the setting that tit for tat was explicitly designed for? So we put it back in a whole mix of other agents. I'm not going to explain them in detail if you haven't seen them before, but the main ones are like tit for tat and also this one win, stay, lose, shift, which is just like if we both cooperate, keep cooperating. If we both defect, that's a loss, so switch. If I cooperated and you defected, that's a loss, I switch. If I cooperated and you defected, if I defected and you cooperated, that's a win, I'll keep defecting. So, and these two strategies had been really kind of like the winning strategies for almost 20 years. Okay, so then what we did is we first just replicate previous results. So when you have this repeated setting, small number of repeated interactions, selfish agents win. As you get more interactions, tit for tat wins. Okay, good. That's a replication. Add a little bit of noise. Tit for tat's not going to do so well because it's not robust to noise. Instead, you get that win, stay, lose, shift algorithm comes back and wins out. Now, when we add our strategy into this mix, our strategy is basically able to outcompete all of these other existing finite state automata. And it's far more robust to noise than any of the other existing approaches. So what I'm hoping to draw from this is that we started with a more complex problem, but we didn't just end up with a more complex solution. We also ended up with a more powerful solution that's able to, essentially do more than previous approaches, not just in the sense of being flexible, but also in the sense of just being a better cooperator, of being better. Okay, and then finally, just to end, the model is able to integrate both its own observations, its own experience, and observational experience, because it's just all about that Bayesian conditioning. So now we're going to look at a case where there's no repeated interactions. Agents just interact once with each player in a unique game. And now we're just going to vary the probability that that interaction was made public. So on the far left, you can see nothing's public. It's all private. Selfish agents win out. But as more of the interactions are observable, agents can do the accounting of the reputations of each other and figure out who to cooperate with and who not to. Okay. So yeah, let me just wrap up. basically the idea, combining some of the evolutionary game theory with the computational cognitive science models is enabling us to start to study how different aspects of cognition are able to drive better solutions to these evolutionary challenges. And then, let me just wrap up. So I kind of touched on different aspects of human cooperation, both in the moment, where agents have to generalize into novel situations, how they learn, different kinds of knowledge that allows for far more generalization across people, potentially during development, and how those different pieces of the models, different pieces of cognition, can be grounded in an evolutionary framework to understand what is most supported by that kind of rational evolutionary analysis. And what I hope is that this reveals, in some sense, small sense, the scale and scope and sophistication of human cooperation, and how it's ultimately grounded in social cognition, the kinds of representations and processes that humans bring to bear. So thank you so much. I know I went a bit over time, and these are all the various collaborators that I've been working with. Thanks.
We have about 17 minutes for questions.
Thanks. Stimulating work. You're of course you're looking at patterns of behavior and trying to infer the underlying computations, and the goodness of fit between those two is a measure of the accuracy of your inferences, and that in some cases you're actually testing by, for example, asking people what they think is going on and comparing that to the predictions of your model to what is going on. It's not clear to me where emotions fit into this. So there are two ways that emotions could be fit into this. One, which some of the people in this room, myself included, have advocated, which is that the emotions are themselves undergirded by these kinds of computations, including priors and updating. Right? But there's another version, I think first put forth most prominently by Robert Frank. Alan Fisk in this department has made a similar kind of argument, which is that there are algorithms making computations, and then there are emotions. And the emotions are computations that have been performed by natural selection, and they often exist precisely because of weaknesses in the calculations. So Frank argues, for example, that things like guilt, gratitude, and even just habit exist because we discount the future, right? And you need to combat that if you want to have extensive iterated interactions that are cooperative. And the byproduct of that is that we are pro-social in situations where there is no opportunity for repeat interaction, because although the calculation is telling us this is a situation to defect, the emotion is telling us something different, right? So I'm curious where you fit emotions into your approach to the problem, and what your response to the Frankian argument is.
Yeah. So I'm very, I'm like on board with that whole, Michael Frank and Fisk's work on thinking, Bob Frank's work, and Fisk's ideas about how that, you can think of emotions as almost like cached computations that are going to be less flexible. But I see myself as just being kind of perfectly able to compose with those theories, because when the alternative here would be to say, well, tit for tat, the agents and the models that we're building are not ones where any of the agents are thinking, I want to do tit for tat because it's a good idea. They just do it. That's built in. And so in some sense, that the emotional level or why you're doing something is going to operate at a higher level. It's telling you what the underlying social strategy should be. A lot of the work that I showed you here is in some sense how to then ground that abstract intention into all these different situations. So for example, it's certain that in evolutionary time, no one has ever seen something like that. But just in my experience piloting this experiment and also the responses of participants, it's very clear that many participants had emotional responses, including frustration, regret, joy, disappointment, when the interactions didn't go as planned, right? So what I would say is that, and all of that is going to then shape how they are going to respond in the future or how they might respond with that particular individual. But it still requires them to do some kind of computation to figure out, like, well, what happened? Why, like, in order to compute something like regret, I'd have to think about, like, well, what could you have done differently, or what might I have done differently that maybe wouldn't have let me get screwed over by you? Maybe that's why I'd feel regret. Or, oh, I thought you were going to screw me over, but you didn't. So, and I screwed you over because I thought you were going to screw me over, but you didn't. So now I feel guilt, right? Okay. So, but you can make all those computations in situations you've definitely never been exposed to. So the emotional level has to operate over some kind of much more flexible, almost like a kind of social perception that gets things into the right primitives for that computation. So that's one. And then two is, in none of the work that I showed did I ever have agents thinking, like, I'm going to be reciprocal because that's what's best for me in the long term. In some sense, I'm taking for granted that aspect of cognition, and there's quite a bit of developmental work from Kylie Hamlin and others, that certain kinds of social reasoning are actually present from as early as 3 months in young infants. The second thing I would say is that the kinds of computations, and this is related to the first, is that, and this is some work that I'm doing with Rebecca Sachs and also another PhD student, Day Hallhan, where we're actually trying to model people's emotional attributions using these same kind of models. So you watch two people play a prisoner's dilemma-like game, and then you have to make the prediction. You see what happens. How do you think they're going to feel about it? And we have them rate a whole multidimensional spectrum of emotions. And we basically show that using these same kinds of underlying primitives related to outcomes and intentions and counterfactuals over those primitives, that we can actually do quite a good account of the way that people predict or attribute the emotions to others. Now that's different from feeling the emotion yourself, of course, but it is related. It is relating to those kinds of ideas. So I guess to sum up, I would say a lot of the work I presented here, I think, is at a lower level. It kind of gets things into the right abstractions that allow us to feel things about what happened in a kind of unified currency of social behavior. But it's not to replace any of those ideas. So, for example, I would say, like, let's imagine. So I had to cooperate and compete, but I might say, like, what about, like, retribution? Like, I would say that needs to be added. We need to add something like that in order to capture the richness. But it's still going to end up depending on, like, how do you move around? Like, what does retribution mean in this game? Maybe it's just like smash the guy. I don't know. So I would. I think that's all just pointing towards places that I can push this further to capture more and more of that richness. So sort of taking a bottom-up approach in that sense. But I think there's a lot more to do. This is definitely not to say it's everything. Yeah.
I appreciated a lot your first slide with ants, because that's kind of what I work on. But I would sort of say that looking at social cooperation in ants, you treat them much more like automatons than anything like what you talked about here.
Yeah.
And I would say across cooperation, across the variety of species in nature, they're more of the automatons than this, which leads me to question, if what humans do is good, why aren't there more organisms out there doing the same thing? Or how do you get from the automaton level to the level you've been talking about for the last hour?
Yeah. All right. So I'm going to enter a pure speculation because I'm not a comparative person, but I would want to argue that it's about these kind of social, the kind of social cognition that humans have. So
so which goes first, the social cognition and the abilities, or the abilities produce the social cognition?
Yeah. So I would say, so by social cognition, I mean things that don't necessarily involve interaction, but are still so distinctly social. So, for example, the ability to do kind of sophisticated theory of mind reasoning, right? To flexibly infer an other agent's goal based on, in a very context-sensitive way, based on the idea that they're themselves a goal-directed agent, to model another agent. So that's useful even if I'm just watching and learning, right? So I kind of believe that those kinds of things come first because they're so useful for building interactive agents on top of it. But I think the evolutionary story is like, well, you can also think about it from the other direction, which is that, the gains of being able to do this kind of flexible cooperation are there, that once you're able to do any piece of it, there's an incentive to develop more and more sophisticated social cognition. So I don't know how to break that that circle. And just to, in some future work we're hoping to do in collaboration with some primatologists, to look with these same kinds of models, to look and see, well, there's some evidence of human-like cooperative abilities, but then of course tons of work on diminished social cognitive capacities, and so to study that with models. So to really look and see, well, what can we say formally about, or what can we say by connecting these mathematical frameworks to the behavior? Can we say, does that explain why they look cooperative but only in these limited regimes, or look cooperative but aren't really indicative of like a true joint intention to work together, to try to move towards a more model-based analysis in a comparative way. But I don't know how to break that cycle. Yeah. Yeah.
I had a question about the first study that you showed, about the MSERG study. I thought from the different games that you showed that they differed in how difficult they were to figure out what the cooperative and the competing strategies would be. And I was wondering whether you saw whether people were more forgiving towards others' behavior in the more difficult games, since maybe if a game is very difficult, the strategy that somebody is pursuing is less reflective of their actual intention, because they're more likely to make mistakes in compared to the easier games.
Yeah, that's a great question. I don't have any formal results on that, but I can say just from my own like reading people's responses or looking at some of the data, that it did seem on, say, like if you remember that weird kind of coordination game that had like different, they had to like, one had to go down for the other to go around, and things like that, it definitely seemed in a few cases that people were unable to, sorry, just turn the volume off. Were kind of, it was, again, like you said, kind of more like if they started off not cooperating, it was less about a reciprocal interaction and more like when one person figured out, oh, I just have to go around you or something like that, then all of a sudden they just did it every time, even when there were mistakes, right? Like execution mistakes, because there's in some sense no intention of, did you want me to win or not? It's just, did we move together in the right way? I also just in the kind of people self-report at the end of the study, a bunch of people in those complicated coordination tasks said things like, at first I tried to just like go for the goal because that's the only thing I could see to do, but then I saw the other person was doing something that looked like we could both get the points. At first I didn't understand, but then I got it and we both got more points at the end or something like that. So I think there is some evidence that like, I mean, I'm kind of arguing like people have this very flexible planning apparatus. You put them in a new case, they figure it out immediately, but it's really not the case, right? Especially because you have this big blank to fill in of what's the other person going to do. And until you start to get some experience with what other agents are going to do, you might not consider the full space, which our model, and that's a limitation of our models. So our models do consider everything that the other agents could do. And so to model that, we would need to kind of think about more boundedly rational agents in some sense. Yeah. Yeah. Hey.
Hi. Thanks for a great talk. So you might know that there's this debate and claim right now circulating in the literature that the use of mental states and intentions and internal states to condition moral judgments and cooperative decisions is not a human universal. In fact, there was just a paper that came out by Joe Henrich and colleagues that you might have seen where they claim that our focus on intentions is actually they blame it on the Catholic Church and claim that actually this is not something that's common around the world in moral systems, and that instead that people's judgments are based more on outcomes, but also your decisions whether to cooperate with somebody might depend just on their social identity, for example, not their intentions. And I'm just wondering what your thoughts on that are as a modeler. Is it, I mean, is it possible in these worlds that you're modeling that you could have situations where that kind of a moral system would be stable, and does it make sense that it would even perhaps be more common than one based on intentions? Yeah.
I think that's really interesting, right? Because, and I think this gets at maybe the first set of experiments I showed with the grids, where like, in some sense, if you just condition on outcome, you're going to do pretty well, and so it really depends on the environment, right? So if you're in an environment where outcomes and intentions are often going to deviate, and deviate in ways that are understandable, I think that's also important, right? So not just like, hey, I screwed you over, but like, trust me, it's all good. I really wanted it to work out, but in ways that are credible, that you clearly had the intention to cooperate, and it just didn't work out, right? Like I showed one example, I think, where the example I showed where the blue agent tries to go in the goal but fails, right? But you could also imagine the other version where both agents are looking like they're ready, they line it all up, they're ready to go in together, and then one agent gets in and the other doesn't. But then you would never, I think it'd be wrong to say, well, that guy really tried to screw me over, right? So I think a lot of that, I mean, so on the one hand, I guess I'm sympathetic to Joe in that definitely the kinds of situations you're going to be put in are going to affect the kinds of, how the way reciprocity is going to work. I don't think I have to argue that if some cultures decided to condition on the mental state, that like clearly then I think everybody has the ability to do that kind of mental state reasoning. That seems fine to me. But yeah, I mean, I think that's interesting, right? Is like, so when I showed the moral learning part, you might say, well, there's not just direct reciprocity. It's like, how much should we put on the direct reciprocity in terms of outcome versus intention, and have those two things be things that are themselves being adapted for? That would be really interesting to look at. And then we could put it in the evolutionary framework and say, well, how does it depend on the kinds of noise and structures that you're going to be in? So a big part of why this particular setup works well when we add a lot of noise compared to, say, the behavioral models, which are just reasoning about outcome, is because they are able to integrate over time about intention, right? So, and about reputation. Like, yeah, so tit for tat, it doesn't matter how long we've cooperated. As soon as you play defect, the other player will play defect back. But in our model, if you played a long sequence of cooperates together, then it's like, well, I'm really sure you're a good person, and if there's some probability that things get switched up in the environment, I'm going to take that into account when you make a mistake. So different environments might even be kind of ecologically rational to set that differently. So I think that was really interesting, actually. Yeah, it'd be cool to explore.
Let me take one more question. I will ask if no one else has a question.
Great. Okay, good. My question. So I was just wondering, really quickly, just about the development piece. How are you factoring in, or are you factoring in the sort of different models and how children might learn differently from adults? Or is it development across time, but not specifically across childhood?
Time, not childhood. Yeah, sorry. Yeah. I mean, I think one way to make it more childlike learning is, I guess, some of the things that we talked about a little bit earlier, is like, you're not just observing a big sequence of observations, but you're getting all kinds of there's actual interaction between generations, right? And that in that piece we didn't really model that. It was just like there's people speaking in the same way of language that you might think about a very, very simplified language evolution study of like there's the speakers and the listeners, and then the listeners become speakers again. That's kind of where we left it. But of course, the interactions within a generation are super interesting that would be needed to really enrich that account. Yeah.
All right. Thanks. Join me in thanking our speakers. Thank you.